Okay, guys, we completed part one this morning of figuring out our collision avoidance triangle, and so we're going to establish or do step two. And so now we're going to find the true course and the true speed of this target ship that we did this morning. As a reminder, our target ship was here at 1400 hours, and we call that R. And he had a range of 11.5 miles at 045. Then 6 minutes later, his range was 9 miles at 043. So from that, we established the relative motion line. Then we established the point of CPA, which again is always 90 degrees to the relative motion line through the center of our target. From that, we calculated his CPA distance, the CPA bearing, and the CPA time. Now we want to establish what his true course and true speed is. All right, I went ahead and put the information here that we're going to deal with in step two, which is we're going to establish the other corner of the triangle. We've established where R is and where M is. Now we have to find out where E is. Now, like I spoke about yesterday when we were talking about the labeling, E, which is the third corner of the triangle, is also known as the origin of the true motion vectors. Just like when you were in high school, when you did X and Y axis, or you did mathematical problems that had to do with vectors in geometry, it's the same thing. When we actually draw on the paper any line that leaves the other corner of the triangle, E, those are true motion vectors. It's the true motion of the target ship and the true motion of our ship. Okay? So that's very important to remember, is that it's a true motion. Now, we have one side of the triangle, which was the relative motion side. The other two sides of the triangle are written up here on the board, and it says E towards R is us, meaning that the side of the triangle that's represented by E to R is our true course and true speed. The third side is E towards M, or them. So we have a little rhyme going on here. E towards M is them. And again, it's the target ship true course and true speed. Okay? Now I purposely use the word towards here. Some people write this down as E and they'll put an arrow M to them. And that's okay, but I like to use the English word towards because it really establishes the fact that it's a sense of direction, and it reinforces our concept that this is a true motion vector. Okay? So, we have to establish where E is. So in order to do that, we need to take a look at our information that's on the board and say to ourselves, okay, what do I know? Okay, I know where M is in the triangle, so I'm going to put a little check mark next to that. And I know where R is, don't I? Now, do I know where E is? No, that's what we're trying to find out. But if I know that we know our information, us. We know our true course and true speed, don't we? It's right here. That's the only thing I know completely is our true course and true speed. Correct? So I can use that information to actually construct the triangle, if you will, backwards. I can place E into the triangle, the collision avoidance triangle, by drawing it in backwards with the known information that's us. So here's what we do, okay? I'm going to take my current course, represented by this line right here. I'm going to take our course, which is 0, 0, 0, okay? And watch me up here. This is important. I'm going to take that course and I'm going to slide it over to R, wherever R is on the board or on your paper. And I'm going to take a line and I'm going to draw it in the opposite direction from R. Okay? I've taken my course, I've slid it over to R because I know where R is, and I'm looking for E, okay, and I use my true course and true speed. So if I take my course to R and draw it in the opposite direction, okay, now I've used my course. Now I have to use my speed. Now how fast am I going?
20 knots.
20 knots. So how far am I going to go in 6 minutes if I'm going 20 knots? 2 miles.
2 miles, yeah.
You're going to move the decimal point, the 1/10 rule, you're going to move the decimal point over, and I'm going 2.0 miles in 6 minutes. So I take my compass, take your compass, and go to your 12-mile scale and get 2 miles, okay? And then physically take that representation on your compass of 2 miles and go from R and go ahead and make a mark on that line that you just drew. And that is where the location of E is. Now, if you watch up here for a second, once you draw this, I want you to step back from it and look at it and say, okay, is this true? E towards R has got to represent our course and speed because it's a true motion vector. So if I look at this right now and I go E towards R should represent our course, and does it?
Yep.
Yeah, because it's 0, 0, 0. And if I measure the distance of that true motion vector, that actual line that's on the paper, and I go and measure it, I went 2 miles in 6 minutes. You see what I'm saying? So it's got to represent the true information. It's a true motion vector. And the origin of E is where it starts. So imagine the hands on a clock spinning around. E is the center of where the minute hand spins around. It can never leave E. And this is important to understand because later on when we go to step 3, when we figure out what new course we have to steer to avoid this guy, I'm going to be taking our course, our heading, and I'm going to be changing course either to starboard or to port. And you're literally on paper going to take this line and swing it to the right or to starboard. Okay? So you're going to redraw this line facing to starboard. Okay? Because it's a true motion vector. It literally represents our heading and our speed. Okay, once we establish where E is, now all you need to do is solve for what we're looking for. The target ship true course and true speed. You take your straight edge, go ahead and draw a line from E, be very precise, through M. Now watch me. I take that line and I bring it back down to the center so I can actually read what that course is. I take it to the center of the plotting sheet and make a little mark out here, and I can say that this is the course, okay, of target A if I wanted to. All right? And we can establish what that course is. So his true course is 286. Now if you want to, this is very important, I want you to do this, is I want you to put another profile of a vessel right here, okay? Because it helps you remember which direction this guy is going in. That's the direction he's actually facing. That's his true course. Now, how do I find his speed? Think about what I said. This is a true motion vector. How did I establish our speed? True speed. So how do we establish the true speed of the target vessel? Measure E to M with your compass. Just take your compass and measure from E to M and go ahead and take it down to your 12-mile scale and tell me what the true speed of the target vessel is. 21 knots, okay? So the length of that line from E to M, okay, this is his true course and the true speed of the target ship, okay, represented by E to M. So that's how we find the true course and the true speed of the target ship. Okay, let me talk a little bit about re-emphasizing our discussion of the true motion vectors. We obviously just took a look at how to find E, and we went and placed E into the collision avoidance triangle, and we found E to M, which gave us our true course and true speed. But let me redraw on the board and re-emphasize this fact that these are true motion vectors. Okay, so let's look at some other scenarios that reinforce this concept. Suppose at the same time you were tracking this guy, we had a target that showed up on the radar screen here. So we went ahead and took a range and bearing like we normally do. We went ahead and plotted it, and so we call that R. All right, and then 6 minutes later we take another range and bearing, and we have a position here, and we call that M. Okay, now you're going to go ahead and do the same process of plotting this target. You're going to take your straight edge, you're going to draw a line from R through M down past the R position on the plotting sheet. We're going to go ahead and label this the relative motion line. So now we see where this guy is tracking. We're going to get our CPA by taking our 90-degree straight edge, placing it on the relative motion line, and drawing it through our position. And this is the CPA. Okay, so we've acquired the point of CPA on that relative motion line. We go ahead and calculate the distance, bearing, and time like we normally do. Then we go to the step that we've just reviewed here, and we're going to find E. So what do? We go ahead and take our course, 0, 0, 0. We're going to slide it over to R, just like we normally do, and we're going to draw a line in the opposite direction. I'm going to put it in a different color here so you can see it. Okay? Now, in actuality, that line is right on top of the other line. Okay? So already, you know, your antenna should be going up and you're worried. Okay? But let's proceed and see if our situation develops here. Now we take our compass. We're doing 20 knots. So in 6 minutes we go 2 miles. We go to the 12-mile scale. We get our 2 miles. Just like we did over here, we're going to take our 2 miles and go ahead and go down from R and place a mark on that line. Now, as you can see, what has happened is that E and M occupy the same exact position on the plotting sheet. So your first reaction is you look at that and say to yourself, man, I must have really done something wrong here. You know, I don't see a triangle at all. But in actuality, if we review and remember our E towards M is them and E towards R is us, and they are true motion vectors, just like you did in high school, is there any length to the vector E to M? There is no length. So numerically, the value of E to M is what?
0.
It's 0, isn't it? So if it's 0, that means that that target is
Dead in the water.
dead in the water. Okay? He's not moving. Okay? And the vector actually tells us that. If it's 0, then he's dead in the water, because there is no length of the vector from E to M. However, the other information is still there. In reality, think of this as a buoy. And you're going down a channel and you see this buoy off the port bow. The buoy is actually in place, isn't it? It's anchored to the bottom with a concrete block. But as you go by it, relative to you, that buoy is going in the opposite direction or a reciprocal course to you at the speed you're traveling at. And that's this issue of relative motion, okay? So if you measure from R to M, just like we did over here, you still get the relative motion, and you can see that that ship is going to go by you and still have a CPA and still have a time to CPA, even though it's dead in the water. Okay? So let's take this to the next step is, suppose when I did all this, M actually was down here. Now what's going on? What does the true motion vector tell you of E to M?
You passed that already.
It's still traveling the relative motion line, but again, remember, E towards M is them. So he's on a reciprocal course. He's steering 180. And if you measure from E to M, for the sake of discussion, we'll say he was doing 2 miles in 6 minutes, so he's going 20 knots, isn't he? Okay? But he's on a reciprocal course. Now, congruently, that means R to M is still the relative motion. So what's his relative motion speed? 40 knots. It's still the length of R to M. You would measure this distance just like you did over here to get his relative motion speed. It's just like going down the freeway. You're westbound at 70 miles an hour, and the other guy is eastbound at 70 miles an hour. Okay? What is your rate of closure of the two cars? 140 miles an hour. Okay? Same concept here. Okay, the last scenario is suppose M actually was right here. Now what's that other vessel doing?
He's moving on our same course at a slower speed.
He's, again, E towards M. That's why I use that adjective, towards. E towards M is them. So he's moving on the same course we're at, okay? But he's only going 10 knots. So what's happening is that we're slowly overtaking him at 10 knots, represented by the distance from R to M. He's still going to go down our port side as we slowly overtake him, but the drawing, the triangle, if you will, is still giving us all the pertinent information. So you're not always going to get a traditional classic triangle, as we say. All right. Now, there's a couple of other scenarios that sometimes you run into, and one may be this, is that sometimes you'll get a target here, and then the next target will be here of that same ship. And so you draw in the relative motion line. Here's R, here's M. Relative motion line. So you drop in your 90 degrees, okay? And you find that the CPA occurred between R and M. So what does this tell you? While you were waiting for 6 minutes to go by in order to acquire the next range and bearing of the second plot, the CPA occurred. So this happened in the past. It's not in the future. Like these CPAs up here for this one and this one are still in the future, and you could calculate out when it was going to occur. Here it already happened in the past, so it's irrelevant. Say this happened at 1400, we'll follow this up here time-wise. This probably happened at around 1403. And then at 1406, you actually took the range and bearing and you plotted them here. So it happened in the past, is what we're saying. Okay? All right? So I hope that helps you understand this concept of the true motion vectors. You're not always going to get the classic looking triangle that we look at, but the data is still here. And it's because these are true motion vectors that orientate from E. And the length of these and the actual direction they're on the paper represents the true course and true speed. Okay? Now, I want to review and back up a minute. Remember that I've asked you to establish the time of CPA up here. And we do that on purpose because when you're establishing the time of CPA, the only speed you know of the target ship is the relative motion speed. Remember we established that earlier this morning? Okay? You have to use relative motion speed in order to determine time of CPA. And I want you to do it then, because what I find is people make the common mistake is that if you do all of this real quick, A lot of people use the true speed of the target ship to find the time of CPA, and that's wrong. You need to use the speed at which he's traveling down the relative motion line, which is relative motion speed. You cannot use true speed to establish time of CPA. So that's how we establish E. So quickly to review, we're going to take our course, we're going to bring it over to R, and we're going to draw a line in the opposite direction. Once we draw that line, we're going to take our compass, find our speed in 6 minutes, which in this case was 2 nautical miles. I'm going to drop down from R and establish the position of E by making a mark. As always, I'm going to label that E, and then I simply measure the angle and the distance of the true motion vector between E and M. That will give us our target ship, true course, and true speed. All right, very good. We're going to go ahead and practice this now for a while.